Welcome everybody. So today our speaker is Mikaela Lacobelli, this year member of the Institute and normally professor at ETH. And she's going to talk about challenges and breakthroughs in the mathematics of plasmas, supposedly plasma in plasma physics and not plasma in medicine, but we'll hear from her. Please, go ahead.
Thank you very much. Thank you for the kind invitation. Today I'm going to talk about plasmas. Yes, as Camilo anticipated, it's subject in mathematical physics and not physiology, but still the name of plasma comes through the the similitude with plasma and the resemblance with the blood plasma. I will explain why that. So the study of the physical phenomena in terms of mathematical analysis goes back to the ancient Greek traditions. So with the works of Euclid, Archimedes, and for us, it's particularly important the first contribution by Democritus, who was the first atomist, who described matter as composed by particles. And this was then somehow debate, and the way of approaching mathematical physics was very linked to the Greek tradition for many long time, because at the time there was not a very clear division between sciences. There was not math and physics and philosophy, it was all together. And this lasted for several centuries until around the 16th and 17th centuries with the scientific revolution and the works of Copernicus, Galileo, Kepler, Descartes, and Newton. And this shaped now the mathematical physics as we know it, as of yet, because what was fundamental was various contributions, but think about, for example, the fact that now we have a Cartesian plan to describe the variables. So, for example, we can consider time as not completely separated entity between with respect to space, but now we can put in a Cartesian diagram time and space and see them evolving together. But in particular, the advent of mathematical physics and evolution equation as we know it started with Newton. He used calculus to substantiate laws of mechanics. And what I recall you is how you can describe a system of n particles. Because when we will talk about plasmas, we are going to talk about many body systems. And the idea is that we want to model the evolution of many particles. So we have a position that we indicate with xi. So this is the position of the ith particle, supposedly in R3, the physical space. Mi is associated mass, and then we have the velocity, that is the derivative of the position, and the acceleration, that is the derivative of the velocity. And we can encode the whole motion of all the particles of the system through Newton's law. So we have that the derivative of position is velocity, and the mass time acceleration is the sum of all the forces exerted by all the particles on the particle I. Okay, but let me point out one first observation is the notion of phase space. In Newtonian mechanics, the phase space grows with the number of particles because the phase space is the smallest space where all the physical states can be represented, and a solution to this equation can be shown to have existence and a good behavior. Okay, and here we need to have all the coordinates of position and all the coordinates of velocity represented for each particle. So of course, the two-body problems, we know there are Kepler law. Then from three-body problem, four-body problems, the difficulty grows very fast, and this is why it's very tricky to model many particles. But I will show how, using statistical mechanics, it's actually easier to model a 1 million particle system rather than a 6 particle system. That's the idea. So the two most important interaction potentials, so let's say the force can be, in many cases, being the gradient of the potential. The most classical potentials are, and also the most physically relevant, are the Coulomb potential and the Newton potential. So the Coulomb potential is equal to the product of the two charges divided by the modulus of their distance, while the Newtonian interaction is the same except for the sign and the fact that I represent the mass and not the charge. And we're going to see in particular the role of the Coulomb potential for what comes after. Of course, feel free to interrupt me anytime. This is a very soft conversation. So Well, now kinetic theory is a branch of statistical mechanics, and it was, as a field, it started with the works of Bernoulli, by the way, is Swiss, like Euler, and we introduced the notion of mean-free path and mean-free time. And mean-free path is the average distance between the fact that two particles interact through a collision or something. And mean-free time is instead the average time between collisions. And then the field as we know it today was shaped by the works of Maxwell and Boltzmann.
So in what context did Bernoulli think about mean-free path?
It was studying gases. Yeah, although this is Bernoulli the son, and somehow after Newton, there have been a lot of development in other areas of math, in particular probability. And Bernoulli's father was one of the founding fathers of probability. So these notions came up together of this describing of many-body system using the laws of statistics, because there have been some works by Galton and Quetelet that observed, for example, the fact that the fluctuation between the average of individuals follows a Gaussian law, and they found this Gaussian law appearing in many different contexts. Therefore, this, together with the development of thermodynamics, took this these people starting discussing this subject more mathematically, I would say. And in particular, Maxwell and Boltzmann, they did a decisive contribution. And who wrote Boltzmann equation was indeed Maxwell and not Boltzmann. And I'll explain a bit more later. So the idea is this. Now, we want to model a many-particle system. That can be a gas or a plasma. We'll explain later what a plasma is. But anyhow, you have a system of many bodies, and you want to determine their evolution at a certain time, given an initial condition. Okay? And the idea is this. If we have many bodies that are identical, then we can use the fact that there are so many, because then they have a statistical relevance, and we can use the statistical laws to give a meaning to this large crowd of objects. This is why I was saying that having 1 million or 2 million of identical bodies is easier to give a sense of, rather than 6 or 7 or 10 bodies. And here we want to consider a system of 10 to the 20s identical objects. Think about a gas, and using statistical mechanics and the kinetic theory. Now let me talk about some key objects in kinetic theories. So, for example, now we don't want to follow anymore the evolution of each particle, because this doesn't make any sense. Because in the end, when we have a many-body system, we want to see, for example, if we have a gas, we want to understand the temperature of the gas, the pressure of the gas. We want to have access to some measurable quantities, okay? So the idea is like now, instead of looking at all particles, that would be impossible, but also not really useful, we look at another object, that is the particle distribution function. This is the main object. Let me write it here just for future reference. This will be the unknown of the system, and it will encode all the state of the system. And it's the density of the particles in the volume of phase space dx and v, centered at x and v. And this is at a fixed time. You can see a picture of this distribution function. And another important notion now, together with the one of distribution function, is the notion of phase space. Because now the phase space will not be anymore dependent by the number of the particles, but it will be the one particle phase space, because all these particles are supposed to be identical. Therefore, you see now that the dimension of our ambient space will not depend by the exact number of the particles. So we traded somehow many ordinary differential equation for just an equation of one object that will be a much more complicated partial differential equation, but on a one particle phase space. And now the idea is, okay, we have many microstates, but we want to, in the end, access to observable quantities, and we want to understand how these two levels are connected mathematically and physics. So with kinetic theory, we also add, for the first time, a precise description of these three scales of observation of nature. So there is the microscopic scale, that is the deterministic Newtonian scale, that is extremely precise, is time reversible, and Newtonian, and with many good properties. Then we have the kinetic description. This is much coarser than the microscopic one, but you can much more, you can make sense of this many-body system in a much more effective way. And here we have the two, let's say, most famous equations. The most famous is the Boltzmann equation. Then there is Vlasov-Poisson, that is what I will talk about today. But at this level, we still don't have observables. We have quantities that make sense statistical, but are not accessible to measuring. While instead, then we have the macroscopic scale, that is the scale of everything that is accessible to physical observation. And indeed, you see here, we have time, the position, and the velocity. And the presence of this velocity accounts for the name kinetic theory. And at the time, it was a very big change because, for example, if you had the fluid, like a glass of water is still fluid, usually, you would assume that the velocity is zero, but if you model that fluid with kinetic theory, then you have infinitely many velocities going in all directions. So this was very difficult to accept at the time, that you had this set of invisible variables that were somehow, it looked like it complicated things. Instead, at the macroscopic level, you usually have the evolution of quantities of this kind.
Use white chalk.
Sorry, yes, sure. I just found the blue one. That are usually, for example, a velocity field or a density, so a macroscopic observable. And here you have Euler equation and Navier-Stokes. So the idea is like also to understand the relationship between these three scales of observation, because in theory you are describing the same object, just at a different scale. So you want to rigorously be able to pass from one to the other. This procedure is usually called many particle limit or mean field limit. You start from the Newtonian system and you want to send a number of particles to infinity in a certain way and recover the kinetic equation. This is also what is sometimes indicated with Sixth-Hilbert problem in the context of Boltzmann. While instead passing through kinetic equation to macroscopic equation is what is usually called hydrodynamic limit. That in the context of Boltzmann or collisional equation usually is like saying that the ratio between the mean free path and the observation scales goes to zero. For us, it will be another thing, but that's a bit the picture of this. And so kinetic theory, for how it was conceived and how it evolved in time as a field, is linked to many other areas of mathematics, because now we're going to study PDEs that are very much linked to the PDEs that you find in fluid mechanics, but they're also studied using methods from probability theory, calculus of variation, and statistical mechanics, and kinetic theory can be applied in the classical sense, but also to quantum mechanics in the concept of general relativity and so on, because it's somehow a framework to interpret various laws of physical world. But let's come to plasma. So after solid, liquid, gas, you have plasma, that is the so-called fourth state of matter. So while passing through from solid to liquid and from liquid to gas is something that is very clear and precisely described from phase transition, passing from a gas to a plasma is something that is not a unique, it cannot happen. It doesn't happen only one way. It can happen because the gas is super hot. It can happen because you have electromagnetic fields on this gas, and you can find it essentially everywhere from stars, the interstellar medium, but also in lightning auroras and many industrial applications. And for us, let me just say what are the modeling assumptions. We are considering a dilute gas. So imagine a gas that is so hot that all the electrons detached by the ions. So, you have this somehow very heavy ions and a cloud of electrons around that will move very fast. And this is why, Sir William Crookes, Sir William Crookes actually observed it first, and he called it radiant matter. But then Langmuir called it plasma because it looked like, the plasma in the blood, where you have the particles floating around. So, and the physiologists were really upset about the use of this name in the context of physics because they said it generated confusion. There were a lot of heated exchange of letters at the time. And then this Sir here is Sir James Jeans, was the first understanding how to use certain equation, not for plasmas, but in the context of galaxies. We'll see Vlasov-type equation. And this is Vlasov, I'll talk about him. So, okay, plasmas are highly conductive now because these particles are not neutral particles. So in a neutral gas, the particles will ignore each other unless they collide. So you have like two particles in a neutral gas. Maybe if they are going in free motion and they don't touch, they will not see each other. And they will interact only through collision.
Brilliant motion.
This is, no, this is just a neutral gas. Model it with Boltzmann equation.
So they move without each other unless they hit each other.
Exactly.
And it's
Then when they hit, well, it depends how you define your collision operator. If it's the one at sphere, they will, for example, in the case of our sphere, they will just move apart in different directions with the velocity exchanged. While here instead, the situation is very different because these particles are charged and they will interact through electromagnetic field. So they are not colliding, but each particle feels the action of all the others. This is why this is so-called mean field model, because there is this collective behavior that influences the movement of one particle. So this is a big difference. And also plasmas, we will see, are very complex objects because they see the many different scale and many different parameters that have huge difference in magnitude. They appear at the same time. So, for example, for people in numerics, it's like the equations that model plasmas are stiff, let's say. So they're very complex to model. And also the plasma is inherently very unstable as an object. But let's come to the mathematical modeling. The most classical model in PDEs that describe plasma is the Vlasov-Poisson system. You see here, I don't know, maybe for people in PDE it's clear, but now we want to see the evolution in time of this density, f of t, x and b. And this object will follow a PDE. Maxwell was the first one to derive a PDE that was making sense for this. And so we have the free transport part, and we have a part that is the acceleration. So these particles will be moving under the acceleration that will be given by the electric field. And in this case, on the right-hand side, there is zero because we are not considering collisions. If you have collisional systems, usually on the right-hand side, you have a collisional operator that here we are neglecting. Indeed, Vlasov and Jeans were the first one to observe that in several circumstances, it was actually useful to neglect collision to have the appropriate model for galaxies and plasmas. So he is the electric field, so it's minus U, that is the electric potential. And as we said, the electric potential is generated by the charge. Now, let me point out something pretty fundamental. I said before that f of t, x, and v is not an observable. But now we want to use, we have the density of particles that is an observable. And is given by the average, so it's the integral of ft, x, and v in dv. And in general, the observables are all obtained by integrating ft, x, and v against some function of v, for example, in dv. This is how you recover observables. So integrating on the velocity against an appropriate quantity. So a very fundamental fact here is that this is a nonlinear equation because this term depends by the function itself. But it doesn't depend, so the nonlinearity doesn't happen at the level of f, but it happens at the level of rho, of the density. This is a peculiarity of this system, that make it also a bit different from what you see in other contexts. And here you have the coupling, that is Laplacian of U is equal to the density of the electrons minus 1, because we are assuming the ions to act as a fixed background. So if you look at the evolution of the electrons, the ions are just not moving. Of course, you can also look at the evolution of the ions. So if you decide to take the time scale evolution of the ions, then the electrons move so fast that the collisions become relevant and they immediately thermalize. It means that they will follow a Maxwell-Boltzmann law, so e to the u. So I said before that the new introduction, the understanding improbability of this Gaussian was actually fundamental, because Maxwell recovered what we now in kinetic theory call Maxwellian, that is a sort of Gaussian rescaled appropriately, that is the equilibrium state for Boltzmann equation. Okay, so we see it here. And now the coupling is also nonlinear. Not only we have the nonlinearity at the level of the equation, but we also have the nonlinearity at the level of the coupling. And this model is very much used in physics, in particular in the study of the ion acoustic shocks, but also the expansion of plasma in the vacuum and the dynamics of rarefied shocks. But let me also talk about some properties of these equations that make them very special.
Sorry, so there were
yes.
two models. The first model, the ions were basically stationary.
Yes, and in the same model,
They were in thermal equilibrium.
yes, in the second model, now the electrons are in thermal equilibrium. And this rho is now the density of the ions, because now F is the distribution of the ions.
Okay, and so from the comment at the bottom, should I think of the second one as being a more realistic?
No, they're both realistic. But since it has been less studied, I'm emphasizing the fact that it was actually studied in physics, but just less studied mathematically, because it is a bit more complicated. I mean, we first did all the theorems for Vlasov-Poisson, and then this came after somehow.
Okay.
I guess the two equations are on two different time scales, right? In a
Yes.
sense, because the electrons
ions
move
are-
much faster
yes,
than the
exactly, the ions.
Yeah.
And this is, the way to pass from one to the other is the so-called massless limit, that you send to zero the ratio of the masses of the electrons and the ions. So that's the idea. But in both systems there are some properties that keep being there, despite the species being electron or ions. One is that this system is time reversible. Then we have conservation of entropy, conservation of energy, and conservation of many quantities. In particular, we have also infinitely many equilibria. And I'm stressing all these properties because for who knows what happens in the context of neutral gas, this is in sharp contrast because, for example, Boltzmann is irreversible. There is this famous H theorem that says that the entropy can never decrease. And this was proved by Boltzmann. And the idea is that here we have conservation of entropy. And so even at the mesoscopic level, we are not seeing irreversibility. While instead, one of the reasons why kinetic theory at the time was opposed is because it was not clear how one could pass from a deterministic time reversible dynamic at the Newton level to something that is irreversible. This was really something very debated. And at the level of Vlasov-Poisson, we will see some phenomena related to irreversibility, but not at this, not like this. Also, we have infinitely many equilibria that is in contrast with what happened in Boltzmann, where everything thermalized around the Maxwellian. So the idea is that for neutral gases, you pass from somehow, even if you have a configuration of particles that is very special, imagine all the oxygen particles all in a corner, after 2 seconds, they will be spread everywhere. So you go from very special configuration to much less interesting configuration. This is not happening for Vlasov. You have conservation of information. And now let's talk about the moment about what are the main question that the community has been studying. One is the so-called mean field limit. So how to derive the equation effectively from the underlying dynamic. This is something I like very much, but I studied less than other things. Then, of course, at the level of PDEs, we are interested in the well-posedness. We want to see under which condition that make physical sense. You have global existence, uniqueness, and stability of the solution. This is clear for people in PDEs why this is important. And also, the long-time behavior is a very fascinating topic, because since we have so many equilibria, in principle, you don't know around which of these equilibria you should stabilize. And in principle, since there is no dissipation, there is no reason why you should stabilize around one of these. Because in general, the increase of entropy is a dissipation phenomena that lead the system towards an equilibrium. If you don't have that, in principle, you should not stabilize. But instead, there is this very famous theory of Landau damping that shows that you actually do stabilize. This was discovered by Landau in 1946 in the linearized setting. It proved that if you are around a homogeneous equilibrium, you perturb it, this perturbation will go to zero and the electric field will go to zero. And this is so-called Landau damping, or violent relaxation in the context of galaxies. And it showed how somehow a sort of irreversible phenomena could happen also in a situation where a priori you would not expect. And then there was a whole line of research that was revived by the works of Moe and Villani that understood that this phenomena was actually persisting at the nonlinear level. And this was a big achievement, a big breakthrough, coming back to the title of my talk, because the idea is that, well, Boltzmann H theorem, where it proves that entropy increase, is a purely nonlinear computation. It relies on the nonlinear structure of Boltzmann, while instead, Landau damping was proven in a linearized setting. So a priori, it was not clear whether this was a phenomena that was still happening for nonlinear systems. And then, since the proof of Moe and Villani, we understood the underlying phenomena for this, that is this phase mixing, there has been also a big development in fluid mechanics in the context of implicit damping, although in fluid mechanics, this phenomena was known before as OR mechanism. And this is very fascinating, and I studied also that, but today I would like to talk about hydrodynamic limits, so how to pass from the kinetic equation to some fluid-like equation in the context of plasmas. So the Well-posedness theory of the system has been started by Dobrushin and Arsenev. So it started in Russia, then it moved to the West with the work of Pfaffel-Moser, Brown, Epp, Jons, and Pertam. So it was a very hot topic in the 90s for what concerned Vlasov-Poisson. But now we know that we have global, classical, well-behaved solution, uniqueness, and there is a very solid theory. While instead, for the ionic model, there was much less because, well, okay, there was the existence of weak solutions and also mostly the study of the linearized system. But then I worked a lot on to prove actually global well-posedness and to bring the theory at the same level of Vlasov-Poisson. So now these two systems have the same kind of well-posedness theory that is necessary to study hydrodynamic limits.
So these weak solutions are unique?
This one? No, not in principle. They don't even conserve energy.
So are they physical?
The weak solution, no. But now we have classical, global classical.
So everything is global and classical?
Now everything is global, in time classical, and we have uniqueness under the...
Global in time?
Global in time, yes. But under the hypothesis that at time zero, your distribution has to somehow decay in velocity a bit. You need to have the so-called velocity moments bounded. And yeah, this is the maximum we can do right now. But this was a somehow necessary step to then study other things, either the derivation from the particle system, but also the hydrodynamic limit. So, because we...
In the second paragraph, you're assuming the ions are now somehow mobile, right? Is that true?
Yes. This is where now the ions move and the electrons are thermalized. While here the ions were still and the electrons were moving.
How do you, what's the source of being able to prove global existence?
What was the key idea? Well, I've not explained it here, but the key idea was to introduce a splitting of the electric field. And, starting from this elliptic nonlinear equation, writing this U as a certain U bar plus U hat, where U bar solve Vlasov-Poisson and U hat solve another PDE, and then studying this additional PDE with a calculus of variation and having a regularity theory of the other PDE. And why that was important? At the beginning, I thought that the most difficult part was the fact that this coupling is nonlinear. While instead it's not really that the only difficulty. The fact is that the well-posedness theory for Vlasov-Poisson, in particular on the torus, relies heavily on the fact you want to control the electric field. Okay, so you want to control the growth in velocity of your characteristic. And the idea is that you use fundamentally the fact that you can write your potential as rho convoluted with the fundamental solution of the Laplacian. The moment when you don't have that structure, the whole thing crumbles. So using that splitting allowed me to have somehow to keep that structure and treat the other part as a regular perturbation. So that was the idea that allowed that.
And it's global in time. And what about, can you just say about the initial condition? Can be anything?
Anything, but it's enough that they decay. So you need that the integral of f of t x v, let's say k,
So some
dx dv bounded with k that has to be larger now than d.
Okay.
That's the only thing. While instead for uniqueness, you need that rho of t and x is bounded. And this is a key difficulty because I said before that you have some conservation. So in Vlasov equation, if you have information on the norms of f, they will be propagated. But that's not true for the norm of the density. So keeping this you can enforce that times 0, but showing that this is being propagated is a big difficulty of the whole well-posedness theory. So that was the situation. But now let me talk a bit about how we can have a sort of hydrodynamic limit for Vlasov-Poisson. What does it mean? So we need to introduce a specific length scale in plasma physics that is the most important in plasma physics, that is the Debye length. Now I said that the plasma is different from a neutral gas. So suppose that you have this box with a plasma and you insert a test charge, a positive test charge. Now this positive test charge will disappear immediately because the negative charge will shield it. This is what we call the Debye shielding. And this ball, let's say, has a radius that is lambda d, that it depends by the specific plasma you are considering. And the fact that this lambda d is very small with respect to, I don't know, the length scale of observation is what make it a plasma. You know, if this lambda d is not small, it's not super small, this is just a hot gas. While the fact that lambda d is super small is what make it a plasma, because inside this ball, you see the single particle behavior. If this is small, then you see the collective behavior that emerged from the plasma. So in physics, since this is so small, it's usually considered to be 0. This is the so-called quasi-neutral approximation. And now we will see why it's called quasi-neutral, because the idea is that if you have this huge plasma, globally, the total number of the electrons balance the total number of ions. So globally, it's neutral. But at the level of that ball, you see the charge unbalances. So it's not neutral anymore at smaller scale. Mathematically, if we keep track of where this lambda d appears in the equation, we will see that it appears in front of the coupling, so in front of the Laplacian. So
What is the tokamak?
excuse me?
There was the tokamak. What's the tokamak?
Yeah, that's good. Well, plasmas are very much used to try to achieve nuclear fusion. And tokamak are these like donut-shaped devices to try to achieve nuclear fusion. So the idea is that now Vlasov-Poisson, as I wrote it there, is with electrostatic approximation. So that means we are neglecting magnetic effects. But to achieve nuclear fusion, you want the particles to collide. And in Russia, they understood in the 50s that the best way to have it is because if you have a tokamak, you have a magnetic field, this will force the particles to spiralize, and therefore it will force the particle to collide and create fusion. So these are like donuts where they put like very strong jets of plasmas. And yeah, that's a very cool thing, tokamaks. Now we have various around the globe, and the idea is that if research goes fast enough, before, fastest than climate change, then it will be very useful. So, okay, this lambda d appears in front of the couplings, and the quasi-neutral limit consists in sending this epsilon to 0. And here you see why it's called quasi-neutral, because the moment where you send this to 0, you have rho equal to 1. So the density of the electrons become constantly equal to the density of the ions. You don't see the charge imbalances anymore. This is the limiting system, that is the kinetic incompressible Euler equation. I'll tell you now why this is called kinetic incompressible Euler. And the idea is that since we are killing the Laplacian, that is a regularizing operator, the limiting system is less regular. And this somehow, this electric field now is just a Lagrange multiplier that will enforce this constraint to hold true for all time. So, and it is linked to rho, but more like a pressure into the Euler. This instead will be the kinetic isothermal Euler system. That is what we get when we perform the quasi-neutral limit at the level of the ions. Even though it looks more complicated, actually it is a bit easier, the limiting system, because there is a direct link between the potential and the density. But anyhow, they're similar, they're generally ill-posed systems, they're well-posed for now, we know that they're well-posed for short time, but there are several situations of where it's proven that they're ill-posed. And now let me show you why these are called kinetic incompressible Euler. So Jan Renier understood this link between kinetic and fluid in the context of monokinetic function. So you have f of tx and v. So monokinetic is this. So your f of tx and v is the product of a density that only depends on space times a delta on the velocity. So it's like you're isolating just one possible velocity for every position. So you can imagine it, you have a Gaussian, imagine it as a incredibly big Gaussian. And I'm saying this because Gaussians are very, very important in this context. So if you integrate that, now F is a solution of the kinetic incompressible Euler if and only if rho is constantly equal to 1 and you solve the incompressible Euler equation. And this formally is super easy to see integrating in B or multiplied by V and integrating in B. And of course, then there was a lot of effort trying to understand when this limit could be proven to be true. And then we started from this very peaked configuration, and then we started fattening those up to have them a bit less monokinetic. And let me say that now we have two very good base theorems that says that the quasi-neutral limit is true, let's say in two situations. So one is like Renier. So analytic framework. And the other one is Antoine Doucet. That can be Sobolev initial data. But it has to be Penrose stable. And the Penrose stability is very central in plasma physics. So now we know that roughly any configuration like this is stable. And while instead configuration of this kind are unstable. So you either need a lot of regularity or you need a bit less regularity but a structural assumption. So these two theorems will be somehow a base for me, because now my research started to try to depart from this theorem and have stability of this quasi-neutral limit around data that satisfies those, or anyhow for much more general initial data.
So Gaussians are good for your stable.
Yes.
But what if I take something which is log concave or convex? Does that work too?
Actually, the Penrose stability in 2 and 3D is not simplified like that. It's a specific spectral equality to be satisfied.
Yeah,
this is just a bit of a simplification.
Okay.
In 1D is just precisely that. So, but anyhow, anything that depends on the modulus of V is okay.
Just the modulus.
Modulus of V.
So anything which is radially symmetric.
Yes. So that's a bit the idea, because this Penrose stability, for example, is central in the proof of Landau damping and also appears in the quasi-neutral limit. So these two problems somehow have deep interconnections. And the reason why this configuration is unstable was already known to physicists. It's the so-called two-stream instability. So when two jets of electrons with different velocity, they hit somehow, they immediately generate a sort of vortex-like this is a simulation that was offered to me by Philze. And you can see that you see developing a sort of vortex behavior. And yes, the two-stream instability is one of the instabilities in plasmas that are known to physicists, but there are many others.
So what is the initial configuration in your picture?
These are these two.
So the red zone
Sorry. Yeah, these two jets of electrons with different velocities.
So the red
is one jet of electron, for example, with the velocity 1, and the other with velocity -1, and then
okay, even though they're both red, but you have two kind of opposing velocity.
Yes.
It's like a shear flow.
Exactly. And they immediately create this vortex configuration that mathematically, so Grenier already understood that. He explained it in a note that this was happening also for quasi-neutral limit, but then it was proved rigorously by Daniel Kwan and Maxine Ray in 2014, and they proved that you have instability. So if you control, if you take an equilibrium of kinetic incompressible Euler, and you take initial datum that is close in very strong norms as strong as you want, but only polynomially with respect to the Debye length. So you control this somehow, this distance at time 0 only polynomially, then you have instability immediately. So in practice, plasmas are mostly unstable rather than stable. And so now what we want to understand is whether actually if we take even a bit smaller perturbations, they are stable or not, and under which circumstances. So the idea was to try to start from these two baseline theorems, so having an initial datum that satisfies one of these two theorems plus a sort of perturbation. And here the key idea was how to measure the perturbation. And to measure the perturbation, we use Wasserstein distances because they're very good when you have to deal with Dirac deltas, so with particles somehow. They've been used since the 70s in kinetic theory, in the work of Tanaka and then Dobrushing. Then it was a bit forgotten for a while, and then now we are using them again. And one reason why they're very useful, let me. So if I have two deltas, one is a delta in 0 and one is a delta in epsilon, most distances between probability measures, for example, the total variation distance between delta 0 and delta epsilon, it's always 2. While instead the Wasserstein-type distance between delta 0 and delta epsilon is exactly epsilon, so the distance of the support. It means that these kind of distances are very sensitive to atomic measures, and also they metrize the weak star convergence on compact sets. If you have never seen them, imagine them as a sort of healthy distance where you integrate against a measure that is a product measure, and that has first marginal mu and second marginal mu. So we don't need to know much more about that, but the idea is that to use this, and so this line of research started in 2017. I will show you where we arrived, but briefly because we don't have much time. So the idea is that I take an initial datum now that has an initial part. So I take now an initial datum that is F0 epsilon, that is a sum of G0 epsilon. So it satisfies one of.
Speaking to one dimension.
This is 1D, but now we have everything. But that's the first theorem that appeared was like this. I will call it H. as H0 epsilon. This is the perturbation. And now the whole idea is how small has to be this is H0 epsilon in this Wasserstein matrix. The first theorem was for electrons in 1D, and we could have this sharp result. So exponential smallness is okay. Polynomial will give a counterexample. So we were satisfied with that. Then, as soon as we went to, yes?
Sorry, so is the convergence there in the one Wasserstein distance?
Yes, exactly. This is in the one Wasserstein. In dimension 2, we had it in Wasserstein 2. And this is because of the different, at the time, of the different stability theorem we were using in one or the other. But now we know that we can prove it in all Wasserstein. So it can be done all in Wasserstein 1 if we want. So here, immediately, we noticed that we needed to take double exponentially small perturbation. And we were not very satisfied with that, in particular because we saw that this double exponential was appearing in something. So it was linked to something technical in the proof. And I'll show you just where it happened, what this double exponential appears. Why in 2D and 3D, Vlasov-Poisson gets much more complicated because the coupling is U convoluted with the fundamental solution of the Laplacian. So in dimension 1, it's different with dimension 2 and 3 when it becomes more singular. So all the theory gets much more complicated in dimension 3. So anyhow, the idea is that we want to have a sort of Gromwall, okay? Because we want to prove that we start from two closed solutions, we stay closed for some time. So the idea is always trying to prove some Gromwall with respect to some quantities. And here we have F1 and F2 solution, ρ1 and ρ2, the associated density that have to be in an infinity, but this is for marginal for now. And then we know that the derivative in time is bounded by the Wasserstein-2 distance of F1 and F2 times the logarithm of the Wasserstein distance. This is unavoidable. So if ρ1 and ρ2 are in an infinity, this is all you get. This is the best you can get. And then when you integrate this inequality, you see the double exponential appearing. So this comes from the fact that if ρ is in an infinity, the electric field is only log Lipschitz. There is nothing that can be done, but maybe something can be done to improve this estimate.
When you say nothing can be done, that you're not, do you have examples where it's false?
What I mean that nothing can be done in the sense that if ρ is in an infinity, then the electric field is log Lipschitz. So the base is
then this method of
the method then can be proved. That is what I mean. I meant that at the level of what you get at the electric field, that is it. But then the method is where we needed to improve, and this is what we do. Because the idea, instead of using Wasserstein distances that are giving the same weight, position, and velocity, now we want to remember the fact that in kinetic theory, we have these two variables, x and v, but they are not the same variable. It's not like having an x1 and x2, because the velocities are inherently different. So the idea is like, now let's penalize the position to get space in terms of the velocity by introducing a quantity that changes with the flow. So now this quantity is very similar to a sort of Wasserstein-2 distance, but we are introducing a weight in front of the position. Because when you differentiate the position, you get the velocity, and usually you can handle that term. When you differentiate the velocity, you get the electric field, and this is where the difficulties arise. So the idea is like, let's now introduce this in a nonlinear way that will evolve with the flow. And if we choose this weight to be epsilon minus 2 logarithm of Q itself, and you prove that you can do all this, then we get to a new bound that somehow is better. So it takes away one exponential with respect. So that's, if you start close, you remain close for longer. That's the idea. And applying this, we can get the sharp rates for dimension 2 and 3 for the classical one. Now, for the ionic case, all the story was way more complicated, but now we can also have the same result. And this was achieved very recently. But that was surprising because for the ionic case, everyone was expecting that the double exponential was actually the minimum you could get, because in the equation there is the e to the u that was always giving this extra factor. So we were expecting to have a double exponential.
So the Riemann zeta function at D?
No. This is where you can still optimize if you want, but I don't suggest it to friends, you know, just to enemies. So now this is the picture.
Is that, so you don't know what the number is, or do you have a?
It's not so, I don't think it's so important,
But-
honestly.
Uh-huh.
I mean, we know what it is. For us, I think it's 11/4 or something.
Okay, so you can compute it.
We can compute it.
It's
It's
not
just that
a-
if you want to make it slightly better, you have to redo everything.
Yeah, no, but I'm
I don't
just
know.
wondering whether it's, you know, positive constant that you don't know how.
No, everything is quantified.
It's quantified.
That. Now is because all this business required rewriting all the theory for Vlasov-Poisson, but in a quantified way with respect to this Debye length. So otherwise, in general, this Debye length is not taken into account in the classical proofs. So we started with this 1D that was directly, you know, the good one. Then we did the ionic case, and we had a double exponential. Then we did again the electrons in 2 and 3D, and we had double exponential. And then with method, we did the first attempt with 4 exponential that was very, very small. And now we have the whole picture. And the good thing is that by doing that, we developed some sort of methods that have been applied to various other situations. For example, this idea of weighting the Wasserstein distance in kinetic framework led to many other stability estimates. For example, one could recover almost optimal rate of convergence from R3 to Vlasov, could be applied also in the context of magnetized Vlasov-Poisson, and also to other kind of stability estimates like Dobrushin-like or mean field limit, hypercoercivity. This has other application. While instead, to prove the result in the ionic case, we had to develop a whole set of new tools that allowed also to prove the quasi-neutral limit. So to derive to the incompressible Euler as a quasi-neutral limit of Vlasov-Poisson for Hydrodynamic solutions. So somehow by doing that, we had to really rewrite the theory, and this is now useful. And also it was a good journey on the overall. And now, yeah, for the classical case, somehow the problem is settled, but there remain a lot of open questions. Also, only in the context of quasi-neutral limit, there is to understand all this business when you have magnetized plasmas. There is much less available, or also when you are in bounded domain, because this plasma, this Debye length, create a sort of Prandtl layer kind of behavior around the boundary, so it's very complicated. So there are a lot of open problems still, and also understanding whether this Kinetic-Wasserstein distance can be used more effectively to improve mean field limit is also open problem, and this I close.
Questions?
So is this single exponential sharp in terms of the theorem? That is, I guess linearly, you were showing that it's unstable. And then is this provably sharp, not by the method, but by the actual statement that is?
Exactly. No, the instability is proved by already at the linear level. Yes, exactly.
So you have to have exponential closeness,
Yes.
otherwise it's not true.
Otherwise, it's not.
Okay.
Exactly, that is sharp.
Then you've got rid of all the multiple
Yes.
exponentials.
Well, yes, now we have just one. We had to kill it one at a time. It took some time.
Okay, with this movie that you showed of the instability, does it just keep spinning like
Yes,
forever?
it keeps spinning. It gets a sort of turbulent behavior, like a
Like kind of
vortex.
chaotic?
Yes, a chaotic behavior. That is where we don't know anything what to do. When the stability starts, is where you lose really the control on at the mathematical level, but also the physical level. Because when as soon as instability develops in fusion reactors, they have to shut it down completely. They cannot go on with the instability because this would damage also the reactor.
Do your models allow for radiation or anything like that? Do your models allow for radiation?
It's not incorporated the radiation. Also, there are no collisions.
That could help, right? I mean,
Probably yes, like a sort of control mechanism. Yeah, that's something we have not yet tried, but it's a good point. Yes.
You have modified the Wasserstein distance with some weight. How's the weight decided?
Yes, the weight is logarithm of the modulus of Q. Now this is the quasi-neutral rescaling, and in this case it's that, but in other situation you have to change that lambda of T. In this case it's nonlinear, but in other situation it can be much easier. It can be just a shift, or can be, so for example, for improving the hypocursivity results, it's enough to write something like you have x1 and x2, then you have a mixed term, and then you have v1 and v2, and then you put parameters a, b, and c, and there has to be an algebraic relation between the parameters. So it's still a Wasserstein distance. This, at this point, is not a distance, okay? Just as bounds from above and below with Wasserstein. But if this lambda is a bit easier, it can be proven that this stays a Wasserstein distance.
But so your lambda depends on Q as well. So
it's like, it's this, you have this, you have Q of T equal to modulus of log of Q of T, this, and then you have to prove that you stay in a regime where you just have,
where you can actually
do that. Yes, exactly.
Okay.
So then, but that is all technical, and I have not.
But that means because you can factor lambda outside of the integral, so you have to invert a certain function.
Exactly.
So you have to be in a certain regime, because otherwise the formula for Q is not invertible. Is that the point?
Exactly. And also you have to stay in a regime where the Q is mod somehow.
But this Q is really the optimizer, right? Overall plan.
Yes, the pi 0 is the optimal coupling at time 0, and this is and these are the characteristics associated to the questions. See?
Pi 0 is the optimal coupling at time 0.
Yes, exactly.
Okay.
Well, these are the characteristics at time t. But you can also have written it with the pi t here and with the push forward notation. So that is not fundamental.
Okay, that is not fundamental.
No, you can rewrite it. I think the fundamental thing is that you have to find the good lambda. And I started with lambda, then I tried various powers of lambda, and then after a while I got to this formula.
And you say you can do it for any W, not just.
Now for every W, but this is also something that I realized very recently, because for a long time I thought there was a deep reason why in 1D it was Wasserstein 1 and 2D was Wasserstein 2, and in the end, no, now we can do it in all Wasserstein. But yeah, at the time, for a long time I thought it was really built in the problem, but no.
Okay, if there are no more questions, thanks.